dis quand c'est bon. Hein, on va peut-être fermer la...
I know.
Okay, thanks for coming. We are really happy to welcome today Professor Peyman Givi from the University of Pittsburgh.
Thank you.
Professor Peyman Givi got his PhD at Carnegie Mellon in year 1984, right? So Pennsylvania, United States. Then you got a professor position at Pittsburgh University. So Professor Givi expertise covers a wide spectrum of mechanical engineering, from large-eddy simulation, two-phase flow, turbulence and combustion. He's a scientific editor for AIAA journal. And today you will talk about graph partitioning and quantum speedup for computational fluid dynamics and combustion. Thanks, Peyman.
1984, I was born, not my PhD. I think that was a mistake. So, anyways, thank you. Seriously, thank you very much for having me here. And and I am with the Department of Mechanical Engineering, and also a member of the Pittsburgh Quantum Institute. And this particular research I'm going to be talking about is sponsored by National Science Foundation, NASA, and United States Air Force. Before going into the technical part, I'd like to talk about a little bit about Pittsburgh. Pittsburgh is one of the really most beautiful cities in the world. I'm not kidding, it's one of the most. You've been there. When were you? Oh, really? Okay. Yeah, it is right. At the base of these two rivers there, and this is where the downtown is. And something about Pittsburgh, the location of it. This is where we are. Well, everybody knows Chicago. We are about 10 hours. 10 hours to New York City. 4 hours to Washington, D.C. in the state of Pennsylvania. And the city of Pittsburgh, the good thing is they are 80% against Donald Trump. 80%. So that was a good thing about Pittsburgh. So the city is, you may not know this, we have 445 bridges, more bridges anywhere in the world. No city, even in Italy, has, as many bridges as we do. And another thing is we are ranked as #1 city, most livable in United States. When they consider many things, the expenses, the cost, everything else. So always the race is between Pittsburgh and Seattle. Pittsburgh and Seattle are all, for #1. So there's been, and the city of Pittsburgh, they call them sometimes they call them Sixburgh, because they won the 6 Super Bowls. Super Bowl is the championship of football, and Pittsburgh has won more than anybody in the United States. Yeah, you guys know Pittsburgh Steelers, right? No? They're like Manchester United, Anyway, so as far as the university is concerned, well, that was the downtown. This is the University of Pittsburgh. This is the building of University of Pittsburgh. It's the tallest academic building in the Western Hemisphere, the second largest one. Largest academic building in the world, but the first one is Moscow, and that building, but half of it doesn't work. Really, half of it doesn't work. Ours is the whole thing works. So the largest University of Pittsburgh is one of the really nicest universities in there. It is very large. In one ranking, I don't know, we are typically like this in the world, in the 40s to 50s in the world. And when they do, I don't know how they do the ranking, especially I do not know how do they ranking the French system, because they're always combining and mixing and matching. So I don't know how. We have about 40,000 now. We have about 40,000 students, and we have something called UPMC. I was telling you, University of Pittsburgh Medical Center. Our UPMC is one of the most famous in the world. like our medical school and our bioengineering, they're in the top 5 in the country. So I hope you never have any medical issues, but if you're in the US, in Pittsburgh, that's a really good place to be. Our department, mechanical engineering, we have a variety of different fields. I guess these are the things what you call groups, you know, and one of the groups that I'm involved in, modeling and simulations, we can actually give PhD degrees in modeling and simulations, you know. So a lot of people coming from other countries, especially, they want to get their PhD in computational modeling and simulation. So it's very attractive for a large number of people. I mean, Purdue has one, Georgia Tech has one, and University of Pittsburgh has one. As far as my own students, you know, I've been doing this business for a while now. Even though I was born in 1984, I still, you know, have had a group of very good students. We don't really, you know, list our master students. We list our former PhDs. A large number of my PhD students, they all have gone to become professors. You know, a lot of them like to become professors. But, you know, a large number of them have been going to government laboratories, including one in France. And then we have some who have gone to industry, aerospace industry. A lot of my work is with aerospace, so they go to those. Now we have some of them who go to software companies like Fluent and Ansys and, you know, Math. You guys use MATLAB, right? MathWorks, one of my students got his PhD, went there. Now, but the new thing is, a lot of the newer students, they all are going to these data companies. Seriously, I had students who, you know, they get their PhD, and then, you know, like seriously, like, you know, this guy who went to Uber, he makes like 3 times the salary of a full professor. So, you know, these data companies, they to hire a lot of our students who do computations, you know, so they're very heavily recruited. So it is, you know, do you guys know Target? You know, Target Corporation? Yeah, Target is like, you know, very department store. So a lot of students are getting into it. So there are a whole variety of them to go to different positions. Okay, so this is about a little bit about background. Now going onto the technical side, as I said, I work in the field of aerospace, fluid, turbulence, you know, chemically reacting flows. And if you really look at what the industry is, you know, I borrowed this thing from NASA scientists where I collaborate. And one of the things they say, if you look at the aircraft, you know, if you look at the aerodynamic and propulsion and engine, that makes a major part of aircraft industry. If you want to fly an airplane, you know, a space shuttle, whatever, you know, aerodynamics and propulsion are the main contributors to the aircraft industry. And if you have a, you know, in an aircraft engine, either high speed or low speed, you know, it's just a very, you know, the complex physics. You have a variety of different things. Everything in this laboratory they're working on is involved. You know, they have, you know, inside of an engine, you have a turbulent fluid problem, you might have multi-phase, you have mixing, combustion, chemical reactions, and trying to understand, you know, all of the coupling of them, you know, then you have a fire, you know, you have a flame there, and trying to ignite it, the heat losses to the walls, and whatever else. It's a very complicated, as you know, I mean, just, you know, here, you know, you have one of the world experts here. So we have a major, you know, trying to understand various aspects is a very complex issue. The way that we deal with this is restricted from mathematical computational viewpoint. That's what we work on. And the way that if you look at with a computing platform, the way it has formed since 1980s, you know, this is, you know, since 1980s when the original computers were done. You know, at Carnegie Mellon, you know, they were always #1, as you may know. Carnegie Mellon, they were always #1 in computational computer science and in, you know, in the US. And, you know, back then they had this mainframe computers like IBM 360. This IBM 360 is less than the power of your laptops that you have. And, you know, back then, all the PhD students, they used to work at nights, because during daytime, you know, the university was using them, so PhD students at night, they could run their calculations. So you see a lot of PhD students of that time, they do not know what to do during daytime. You know, in the nighttime, that's where they do their work. You know, as you may know, in the 1990s, they went into the parallel computing, you know, that people learn how to do starting to do vector computation with the craze, and then moved into the parallel processes, and now we are at the point that, you know, we are getting into the massively parallel, you know, to the, you know, we are already past the petax scale and going to exascale, you know, what we want to do with those when we get to that level, what kind of computation we want to do. So one of the things we have done, you know, trying to take advantages of the supercomputing power. And, you know, the stuff that I present to you, although it is in turbulence and combustion, but it really has something in all areas of science. I think it can be used. So the way I put this talk together is, you know, the kind of computation we do could be used for any purpose. Now, my research area is on large eddy simulations. You know, large eddy simulations of turbulence and turbulent combustion. And, you know, if you have taken any you know, any basic course in turbulence, you probably have heard of Reynolds average Navier-Stokes, RANS, you know. And RANS, you know, that's the way industry is. If you know, companies like Fluent or whoever, they're using RANS. And, you know, the way that RANS and LES, they compare, and in LES, you average over the large scales of the flow, and in RANS, you average over all the scale. So the problem is that if you look at like a simple swirling flow, this is like a simple baseline swirling chemically reacting flow. The RANS may do a good job for non-reacting flows. You know, RANS and LES, they do pretty much, you know, a good job for simple, these are simple flows, a simple swirling flow. But the moment you turn on chemical reaction, you know, the standard methods that are in RANS, they are incapable of predicting it. I mean, that's what people know. I mean, people in combustion, in chemical reactions, they know that, you know, a lot of these turbulence models are not appropriate for chemically reacting flows. So, and I think and I'm going to show you the model that we developed seemed to be one of the best in the world, you know. So even though the French group may disagree, but you know, so we'll show you, you know, the method that we have developed is one of the best that there are out there. So to show you the method, I'm going to start with the basic equation of turbulent combustion in a very simplest form. Navier-Stokes with a, you know, a Newtonian fluid with fixed law diffusion. So I have equations for the continuity, momentum, energy, and a species with some sort of chemical system with the simplest form of equation of a state. The simplest form of those equations. We can consider, you know, more difficult equations as we want. But for the simplest one, in LES, we pass these things toward the filter. You know, we take a variable, you know, variable could be f, and we multiply by some filtering function, you know, filtering function g, and we look at this filtered field. You know, the filtered field is a lot smoother, you know, and that's what happens when you go, you know, now with the people, with kids, you know, with the pictures, they take a picture, they filter it, right? If you filter me, you know, me and Alain Delon would look like the same, kind of, you know, I can make my, do you guys know who Alain Delon is? Okay, I'm glad. In the US, nobody knows who he is. Alain not anymore. He's still good looking. So if you filter, anyway, so this filter form of the equations are smoother, and you can perhaps in engineering has argued that you can calculate that a lot easier. So if you pass this thing, you get the filtered forms, and you pass your equations through the filtered, you get the equation for filter, but in this filter form you get a lot of these terms that are unclosed. You know, this term that you require modeling. These are the correlations between the subgrid velocities, velocity and energy, velocity and the scalar, the average form of the chemical source term, and these are all the terms that you need somehow to model. Yeah, right. So Yeah, this one has ui uj minus this. So that's the way they consider all the correlations. Right, and if you are doing RANs, that term would be u prime I u prime j in RAN. And the same thing for this, and these are the dissipation and dilatation of the pressure. And modeling of this term, there is, but epsilon, because when I look at for the energy, this epsilon has a negative term. Right, the negative. But you said the way they do on pressure dilatation and put plus the dissipation in the energy equation for the, because this E in here is the internal energy. You can write them in a different form of energy, then epsilon can appear as a negative or positive. Now, you can try to write equation for the second order terms, all those terms that you need closure for. You can write, and the equation quickly would become very complicated for these correlations. You need model of the higher order term, and makes it very difficult to close this thing at some point. So the method that we developed, and I work on this method in collaboration with Steve Pope at Cornell University. Steve and we come up with this method, and this method we are calling it filter density functions. And I will show you that this method seems to be one of the most powerful methods of dealing with those correlations. So what we decided to do, we said that filter density function, we are looking all these correlations that we need to calculate, we look at their probability density function. Because you are worrying about the fluctuations, so we said, okay, if we're looking at the correlations, fluctuations, we look at the probability density function of the entire thing. We look at that, and we try to find equations for it or model it or whatever. So what we decided to do, we said that for any function, Q could be a function of velocities, scalars, pressure, and the energy. That's what in a compressible reacting flow is. Everything's function of velocity, all the scalars, the energy, and two thermodynamic property, pressure and energy, or any other two that you like. And if I know the joint PDF of all this, any variables I have, I can multiply by those joint PDF, and then, and I know everything about the subgrid. That was the fundamental idea, the mathematics of it. And then we can write a transport equation for this quantity. For
between the subscript small l and the subscript big L.
Right. This one is just a filtered average. This is density weighted average. In a reacting flow, right. Let's see. See, in reacting flow, typically you average them, and then in combustion, or if you have heat transfer, then you density weight them with a capital L. That's what they. And of course, if the density is constant, they both become the same thing. Now, what happens? You can write the transport equation, an exact transport equation for this, and this is a little bit involved to get to this point, but this equation, the beauty of this thing is the effect of convection appear in a closed form. You don't need any modeling for it. And also the major advantage in chemically reacting, the effect of chemical reaction would appear in a closed form. What does that mean? It means that if you have a model that works good for a non-reacting flow, if you know the model is good, you can exactly use that model for the reacting flow, if you could come up. So if you develop a good model for mixing, and it is very good for mixing, it's completely correct, then going to chemically reacting flow, you don't need any additional model. So that's the beauty of it. The disadvantage is this method, all of these quantities that are given by these bars, they are called conditional averages, and they need to be modeled somehow. They have to be, you need model for those terms. You need to have a closure for them. How do we model this? And the way that we are modeling them with this FDF modeling, we look at this whole thing and try to look at them and write a stochastic differential equations for it. So we look at for the whole thing. We look at the velocity, the scalars, energy, the pressure, or any other two independent thermodynamic properties. And for this vector, we try to write model stochastic differential equations for them. So whatever the differential, and the way that we model this D and B, this is what our turbulence model is. And this is one area that actually you can see that in Europe, especially France, they're way ahead of United States now. If you look at within the past 20 years, there has been major development in the US, in doing computations, numerical method, chemistry model. I mean, the way the algorithms are, computational algorithms are. Now we are using a large order discontinuous Galerkin spectral element. They're very high order. I mean, the methodologies from 20 years ago are completely, which is just totally different class. The same thing would go with computations. The way the exascale computations are, they're by far more powerful. The same with the chemistry people who do chemical reaction in combustion. Now they have very sophisticated method that they do for like methane or any other hydrocarbon combustion. But if you look at the turbulence modeling, there hasn't been anything done in the US. All of the good people who have been in this field, like John Lumley, Charles Speciali, Dale Talby, they're all either dead or retired. I mean, so there isn't any more work being done, but whereas in Europe, they seem to be a lot more interested in it. But anyway, so the... None. They're model. They're all model. You have to model them. Yeah, I'll show you. Yeah, that's... Right, I just put them in here to indicate these are vectors of these quantities, and the modeling of them, it is not a lot of science, a lot of arts. A lot of arts of these turbulence models are, people like Lumley or others who come up with this, like, like mixing models, that, Right, somehow you have to come up, and I'll show you, for example, how. But anyways, once you, and this is a stochastic, this is the Wiener process. If I take this thing out, the rest is ODEs. And if this time it becomes, SDEs, a stochastic differential equation. And associated with this one, we have a Fokker Planck, and once you model them, this Fokker Planck becomes your modeled equation. That's what the equation would become. So for example, an example of, as you were saying, example of a stochastic model. So for example, for the, this first one is what Albert Einstein proposed, for diffusion. You have convection plus the diffusion has basically the random walk. And this particular, model, came out, for example, for the velocity. And there is a lot of physics I could talk to you with the whole semester of, how to model the velocity term that somehow affect the effect of pressure, dilatations, and everything within the subgrid, how those models would come in. So that was the turbulence modeling coming. For the scalar mixing, there are a whole variety of methods. This particular one called the least mean square method that pushes everything toward the mean value. So this is where the physical model would come in. And there is a lot of, as you know, France has been one of the leaders in developing variety of turbulence models for mixing and, for hydrodynamics and whatever else. So this would come in. And since, as I said, since we developed this method, many different groups, they have used their own models into it. As you see, within the past 10 years, many different groups at Stanford and others, they have used this format, but they use their own models into this process. And once you do this thing, then you come up with a long Fokker Planck equations that has all of those models in it. And after you integrate this, you have everything within the subgrid. They're all statistical, but you have a model for the subgrid. So the only oh yeah, and of course with this model, again the chemical reactions would appear in a crossflow. Okay, so this modeling part is one thing. It's just good that you do the model. The problem is how do you solve it? So even you have a good model, how do you solve this thing? And typically we do these calculations. These calculations we do. We have a you know, typically we have an Eulerian grid point, so like a complex, you know, any geometry, you know, combustor or whatever. We have a, you know, this geometry with, you know, typically you have finite difference, finite volume, or finite element, the spectral, depending on the situation. If you are doing lower speed flow, high speed, whatever, you discretize the flow in a different, you know, so depends on what physical flow problem you are dealing with. And what we would do, our PDF, we represent them by Lagrangian Monte Carlo element. So each one of these particles that you will see is a Monte Carlo element, and each of these has information about everything, about the velocities, composition, you know, pressure, energy. Each one of them would carry information about that. So typically what happens right now, we have order of 1 billion grid points, typically that's the LES thing is, and order of magnitude more on MC particles, even if you use reduced kinetics. I mean, we are nowhere close to detailed kinetic. If you use reduced kinetics, order of a 20th step kinetic, they are very, very expensive calculations. You know, so, you know, this kind of calculation, they are, if, for example, if you have only like order of 1 million grid points, this many particle, only this 19 species is very modest in combustion system. Modest, you know, one set of calculation on this kind of a machine is going to take about 3.8 years, one set. And this is not, PhD students don't like that. You know, one set of calculation, 3.8 years, and if you make a mistake, you have to run it again. So, you know, it kind of, you have to do something, you know, to help the process. And that's what seriously at the beginning when we developed this methodology, even though, you know, in combustion field, there are many other methods people at Stanford have developed, you know, some people there like, you know, Terry Poinsot, he had developed some methods here. And those methods are a lot cheaper, That's an example. We haven't done it, but we said that how much it would take. That's an example of, if you just do this much, you know, how, I mean, for example, you could do this and extrapolate. If you want to go to this is how long it's going to take. Yeah, there is no way you can get a supercomputer to the 3 point. Yeah. To get. Right. But we want to have something that to be order of hours rather than order of days or weeks or whatever. So that's what the idea was, you know, to develop methods of how to deal with this issue. A lot of engine companies who wanted to use our method, including ANSYS, because ANSYS now they have put them in the Fluent code, they said that, well, you have to make these computations more feasible. And, you know, one of the things we had realized is that, you know, if you have a combustion system, we have regions of, you know, a lot of activities, you have a flame, a lot of things going on. When we divide this domain and to give them to a supercomputer, we have regions and we have no activities. So, you know, and, you know, in Pittsburgh, we have Pittsburgh Supercomputing Center. It's one of the NSF centers that are right in the city of Pittsburgh. And when we talk with them, you know, and that's the way, you know, we do those kind of calculation. A major, you know, when you see things like this, it's a major load imbalance issue that we have. So, and the problem of it is, and this is nothing serious, as it can be in any other field, when we have local interactions, these parallel computations, you have to be very careful. So just to simple calculations, if I have a domain like this, these are my finite difference point, you know, and you have a Monte Carlo particles you put in them, you take the domain, divide this domain into a, you know, number of subdomains, right? That's the way we do, and each domain go to a different processor. That's the way typically these calculations are done on a, you know, large number of processors. The problem with them is, if I'm non-reacting flow problem, things are scaled out very easily, but when it is reactive, because of the chemistry is a local phenomenon at the molecular scale, this is what we get. You know, you don't get a scale up. I mean, and this is not just our issue. Anyone who is doing any kind of a chemistry calculations, they know it. That whenever you do chemistry, when you do this kind of a putting things into the different processes, that kind of a problem that you get. So, yes? It depends on what situation is. In a lot of these things are highly variable density. Yeah. Oh yeah, this particular one, yeah, because this is a flame. Whenever you have, you know, temperature.
But for the equations, is that purely compressible?
We have done both. Yeah, if it is. Right. Yes, yeah, the scaling is the same. The scaling chemical reaction, if it is incompressible or highly compressible or even high speed flow, the same problem. It is the issue of the chemistry. Right. It's the issue of chemistry with that. And then, you know, some of the problem of chemical engineering, assumption of incompressible flow is that, but the chemistry is still an issue. And when it comes to, like, you know, high speed, you know, like scramjet calculations, it is fully compressible with shock waves, and but the chemistry is the same problem. Right. So, as I said, the student who was working on it, he's the one who worked at MATLAB. He's really a genius computational person. And, you know, he said that, well, the way that we want to deal with this thing, we want to associate some sort of a work with each one of these nodes. This node could be like finite difference node, or it could be one of the collocation points in a spectral code, or it could be within one of the elements if you are doing finite element. So you just define those nodes, and if you don't have nodes, whatever method that you have some regions of space, and associated with each one of them, you assign some sort of a thing that measures the amount of work it does. So for example, we are looking at this point, and we look around this, and you see that how much time does it take to do chemical reaction and mixing? Just mixing a reaction, because convection and diffusion doesn't take that much time. Convection and diffusion can be done easily. Mixing can be done easily, but the chemical reaction takes a lot of time. And he said, as we are calculating this, then we are doing it adaptively, divide the work to the different processors on the system, but we do it in a dynamic fashion. The idea seems simple, but the implementation has been very difficult. You know, and because, you know, when this work was done, a lot of people have been in computer science, they have been heavily interested into this. So to just show you how the thing would work, this is in one step, in one time step, this is how the domain does. And I put them together to just demonstrate it. In one time step, each one of these processes would take different amount of particles and finite difference or finite element point, in such a way that they all do the same amount of work. So, and the way you optimize them in a computer science manner, this is what you get. You know, the wall time per number of processes. All of these people are working the same. And this is the way you want your lab to be. You know, all the students are working, you know. And this was the way it used to be. And this is the way my lab looks like, you know. Some of the students working hard, the other students are usually basically having a rest. You know, so that's the way. Only a few students working, the rest are sleeping or whatever, drinking coffee and wine, you know. But this is the way, if you do this, then you can have everything distributed, everybody is working, and, you know, it is a lot more productive. So, I mean, and the idea was, I mean, this graph partitioning, I think that is a way of doing future calculations, especially if you're doing massively parallel. If you're doing exascale computation, there is no other way. Seriously, there is no other way to do anything else. You can't just do a statics to per processor the way people do them now. So this is the way it used to be, unbalanced. This is the balanced ones are. There are some way of dealing with it, but they're very close to linear. And the good thing about this thing is, now we can do the calculations a lot easier. This is a premix flame. This is a premix flame of Norbert Peters. You know, his famous flame. And these lights that you see, like a disco nightclub lights, you know, as this thing is going, these are the different processors. You know, things going to different processors at each time. And, you know, the comparison with the data for this particular flame. This one is a non-premix flame. This is the non-premix flame of University of California at Berkeley, a famous flame that people wanted to compute it. And, you know, and then we have the typical practical combustor. This is the Dlr Flame. You go to the international symposium, the Dlr people trying to predict here at Fairfax, people trying to predict this flame as well. And you know, this is the way this methodology can capture this flame, comparing with the data, not only the statistics, but also the compositional structure. Yes?
How often is the load balancing, how often needs to be done the load balancing?
Yeah.
Like each time step, each bunch of time steps, because I guess it kind of depends on the temporal scale of the problem, right?
Correct, correct. Very good question. So this is the key question, and this is how often you do it. You have to balance it. Even that has to be balanced, because if you do them every time step, the amount of time that it takes to do this might take away from your computation. And if you wait too long, then it loses its thing. So typically, you know, depend on the time scale of the problem, you know, the chemical time step. You want to do within the characteristic chemical time step, you know, that you do a few of those time steps. But there is, right now, we don't have any, there is no scientifically trying to optimize it. At least we don't know that. But there are some people who say that it is possible to do this by means of some artificial intelligence, trying to calculate, to try to optimize it. Right now, we are just doing it randomly, a few time step. Sometimes taking too long. We just do them after, you know, after maybe 10, 20, 100, whatever.
In your opinion, how much does that depend on the type of model you choose for your PDF discretization of the subgrid?
It doesn't have so much with the PDF. It depends on the chemistry, the kinetics model. It depends primarily kinetic, because the PDF method for convection, diffusion, and mixing, they don't take that much time.
No, what I was thinking about is that those are actually changing the local property of the fluid, and then maybe influencing combustion and chemical reaction.
Correct.
So I'm actually thinking that if you have a model, a PDF model of the subgrid, which is changing very often compared to the simulation time step, in a sense, you actually have to update this load balancing quite often, right?
Right. If you are doing very highly compressible flow, that you have shock wave, that your characteristic time, so then you have to do them a lot more often. But if the you know, if you have a fluid dynamic thing like a typical hydrocarbon, the fluid dynamic can relax for a little bit, then you do the, you know, the larger number. But you know, this is the key question on this: how often you do it, and you make sure that you be, you know, because if you don't do them, that's fine. It's just computation take longer. There is no accuracy issue. You know, oops. You know, there is no. It is not right. This is not like a method. Wow, if I write 100 time steps, my accuracy gets less, because the accuracy is the same. It is just a load balance and. Yeah, good question. Okay, so now that this one, the practical competition with this method could be done, but now there is other things. You know, going back to this one, and this is what the second part is. You know, as we are moving to this thing, we are getting to the end of this, right? I mean, the supercomputers cannot get any more super, right? I mean, they're just you know, China has the top 2. But every year they want to make it better, it is becoming a lot more difficult. It's a lot more difficult to make the supercomputer. And, you know, and if you look at this whole idea of classical computers, the way that we are using, you know, all of these classical things are all equivalent, but some of them are faster than the other. That was just the whole idea. They're all based on the same system. And all of these classical computers are all based on this information technology of transistors, you know, and these transistors, you know, if you look at them, they're getting smaller and smaller. And now the transistors of today are smaller than the ATOP influenza virus. I haven't seen this, but people tell me that it is smaller than virus. You know, I have to believe it. And if you look at the Moore's law of transistors, either prices or sizes or whatever, you know, it is just different figures of it or things. But people are saying that we have already reached to the end of this end of Moore's law. I mean, to make them any better, you know, it is becoming almost impossible. So what are the departures from it? What are the possible departures from these things are? Is that there are a variety of ways that people have thought about, and one of the ways of thinking about doing these computations, we talk about the quantum computers, an idea that was initiated in the 1980s by Richard Feynman, a physicist. And his idea was that, you know, if you have a quantum computers to do quantum problems, have a quantum, you know, because, you know, quantum problems are difficult to simulate on a classical computer. So the idea was you have a quantum problem, do it on a quantum computer. So that was the idea. And you know, so this is what we do. Classical problem. We write classical algorithms, and the way that all of our algorithms we write things for everything that we do, matrix inversion, ODEs, PDEs. These algorithms are devised based on classical system. Even when we are solving Schrödinger equation coming from quantum state, we solve those equations by classical methods. That's what are inefficient. You know, you have a large number of degrees of freedom. Those are inefficient. So the idea is, you know, if you have quantum problem with a quantum algorithm, you solve them in a quantum computer. But the idea is, how about if you have a classical problem, right? As an engineering, or, you know, engineers, we're dealing with some classical problem. How do we write those methods? How those methodologies would develop, and if they can be developed, how much faster they are than the classical system. Now, in a quantum information, you have a classical problem. You know, classical information are stored in bits, right? Everything is stored in bits, zeros and one, and quantum information is stored in qubits. You know, qubits are the vector space of 1 and 0. This is vector space in a quantum physics language. This is the vector space 1, vector space 0, and a quantum any kind of a physical phenomena for a qubit is in a superposition. Superposition 0 and 1 at the same time, right? Superposition 0 and 1. Then people say, how can it be in the 0 and 1? And I say like this, you know, 0 and 1, anything, you know. It's just like a lot of foreign students that we have in the U.S. Really, I noticed them. I asked my foreign students, would you like tea or coffee? They say yes. So what do you mean yes? Which one, coffee or tea? They say yeah. So this is it. You know, you want coffee or tea, and the answer is yes. You know, it's going to be 0 and 1. You know, 0 and 1 at the 0 and 1 at the same time. And you know, the way that the spintronics would work for a quantum machines is that, you know, you have an electron, the spin of 1, you know, you can represent it as vector 1, and, you know, going down would be vector 0. And the way people represent it, typically on a qubit, they represent them in a sphere. They call it the Bloch sphere. So the classical bit is 0 and 1, off or on. That's it. Off and on. That's what it is. You know, you turn it on, you turn it off. There's very simple. And this is the brain. You know, this thing can be anything between 0 and 1. Anything could be done at any time. You know, a combination of these two. You know, at any time. Now the thing of it is, this is only for one qubit. With one qubit, you have a zeros and 1, and and this is the state. Zeros and 1, and this one is squared, is the probability being at 0, this is the probability being at 1, the summation is 1. This is with only one qubit. Now if you add n qubits, every representation could, because, you know, each one of these 0 with all the ones, zeros and 1, you have 2n minus 1 of those. 2n one of those that you can represent this thing with. So if you have only 1,000 qubit, which is seems very simple, 1,000 qubit, this thing, n to the power of 300, thing is more than the number of particles in the universe. I was surprised that's it. And I asked my physics friends, they said, if you don't believe it, go count them. How many particles in the universe there are. So that's what it is. So that could be a representation of a physical system. So, you have a velocity field, a composition, you can represent them in that the enormous number of computational power that you would have. Right now, if n is 50, and Google and IBM, they're all building them between this year. With 50, if you can do exact calculations the qubit with 50 qubit would be faster than any supercomputer we would have. You know, any supercomputers up to that with only just 50 qubit. So quickly going, you know, how does the operation work? The operation is that in a classical computer, we give the information in zeros and one in bits. We have classical gates, always AND, OR, XOR, whatever, and then you get the output. Output comes in bits. You read them. You're done. In a quantum computer, the state coming in a quantum state, and we now in here we have gates, quantum gates, that they do a lot of unitary matrix manipulations. These matrices involving things, and then you get the result, the measurement coming out, and then that was what you read. That's what you read. But you have to be careful how to read, because whatever you read, that becomes your reality. You know, so that becomes an issue. Some of the ways, some of the known algorithms that have made the quantum algorithms or quantum calculations very popular. The initial one, Shor algorithm in 1994, that basically was for factoring a number, factoring a large number to a number of, you know, this multiplied with this. I mean, going from here to there is easy. Going from there to here is very difficult. The basics of encryption. So if this thing works, be careful with your bank accounts, because, you know, the encryption could be easily broken easily into it. So that was one of the things that made the quantum computations to be a lot more popular. The second one was the Grover algorithm, that you start to read, you know, to find a reverse way of finding the phone number of people. You know, if you have a number, you find the name. This is the number at that time on a classical, and on a quantum, you know, is much faster. So we know this, and this is what people have known for a long time. And the issue was, and that was the Department of Defense in the US, they asked us, you know, okay, we know this. Can you do something for turbulence of fluid? You know, we don't have quantum algorithm. We have a lot of quantum algorithm. We don't have quantum computers. But if you had one, could you help us? And we asked them how much was the grant size. And the grant was a lot. So they said, yeah, sure, we could do it. You know? So, so the way that, and the problem we started, and I have to say, you know, we had a very good group of physicists, theoretical physicists, quantum information, and we wanted to do a simple problem of turbulent mixing and reaction. So we look like a plug flow reactors, reactant when coming and going, and we look at the homogeneous turbulence. You know, initially the PDF of a composition is a delta function and a fuel and an oxidizer, and we only looked at homogeneous turbulence. We didn't worry about the special variations, everything function of time only. So in this one we have a PDF of the scalars. They have its conditional dissipations and the chemical source them, and we wanted to analyze this thing. We wanted to know if a quantum algorithm could be helpful in solving this, and if it could be, how much speed up we would get. That was the idea. The problem has a large number of applications. Of course, in combustions, you have the word that's spoken here, can tell you everything about chemically reacting fuel and oxidizer. A lot of problems, simple mixing has a lot of application in chemical engineering. A lot of people are interested in it, in drug delivery, atmospheric sciences. So if the method could be shown that can be benefit from quantum algorithm, it can have major impact. So the method that we had used was, again, the turbulent mixing with chemical reactions. We used a typical mixing model that's called coalescence dispersion. Basically what the model does, you know, if you have a chemical reactor,